We are recording.
Fantastic. All right, who wants to learn about pH?
Aye.
Me.
Aye. Motion carries. All right. So Joe and I are going to do this a presentation. This is I wanted to do a presentation for a while about pH. Some of the more technical aspects of it and whatnot that I think are taken for granted or just totally misunderstood. I'll be taking some of the more theoretical stuff, and then Joe's going to kind of give more of a practical how to take this home to your brewery aspects. So hope this works. I'm going to share my screen. There we go. Everybody see that?
Mm-hmm.
Fantastic. Here I go. I'm a lot less nervous about doing this presentation because there's only like 15 of you. So since we have such a small group, if you have a question, just go ahead and shout it out. And if I know the answer, I'll try to answer it. All right. So pH from the brewer's point of view. We're going to discuss just real quick feedback. You guys can still hear me?
Yep.
Okay, fantastic. So in this, I hope to discuss with the pH discovery, the math behind it, what buffer range and conjugate bases are, pKa values, enzymatic function, conversion from starch to sugar, and yeast health and inhibited bacterial growth. We'll kind of touch on all of that. So first of all, discovery, Soren Sorensen, true name, passed in 1939. So in 1909, Sorensen introduced the concept of pH as a convenient way of expressing acidity. Funny thing about pH is I was told in school, like in high school and junior high, pH stands for potential of hydrogen. Totally not true. That's not what it stands for. It's lower p, uppercase H. So it's the inverse log. In math, lowercase p it denotes the inverse log 10 of something. So this is denoting the inverse log 10 of hydrogen ions. Moving on. Also, doing research for this talk, Alice Catherine Evans came up. Now, she passed pretty recently, I mean, as far as like, 1975, but she was around the same time as Sorensen. You could argue that they both made similar discoveries around similar times. So she actually did her work at the UW on pH, but with dairy interaction. If anybody gets some spare time and wants to look up a really interesting character, Alice Catherine Evans deserves a lot of thank yous from the science community. Moving on. All right. Everybody see that? It says math?
Yep.
Fantastic. All right, so there's two ways to calculate pH, and it's kind of like that they have you do in school in food science. We had to be able to do this. It's like if you have the pH, it's a lot easier to go back into the log version of it. So basically pH is the inverse log base 10 of hydrogen ions. Now, can you guys see my cursor?
Yep.
Oh, that's going to make it so much easier. Okay, so 1.4 times 10 to the negative fifth, that refers to how many ions are, how many moles per liter there are, or like the concentration in a solution per liter. it gets really complicated. The math gets kind of complicated because when you take scientific notation like 1.4 times 10 to the negative fifth, that's really easy to figure out. You just move the decimal place like 5 times this way. But when it gets really tricky is over here, like to figure out your concentration, it's 10 times 10 to the negative 10.74. So 10 to the 10th is 10 times 10 times 10 times 10 times 10. So what's it mean when something's like 10 to the 1.4? It gets really, really weird. And when I took algebra and we were learning about these kind of things, my professor is like, absolutely nobody can calculate that like in their head. And he showed me a book that was just full of like 10 times 2.1, 10 times 2.2, 10 times 2.2.2, or 2 point, it gets really, really complicated. Absolutely nobody figures it out on their own and they just use a computer for it. So that's how you see like this 10 to the negative 10.74 just shakes out like that. Moles. So speaking of moles, oh, okay, here a little bit more about the log scale. So since it's a log scale, it's 10 to the negative 4 is, it gets really kind of confusing when you start going by powers. But because we're going by powers, if you can see right here, pH of 7, everybody knows pH of 7 is like, middle of the road, not acidic, not basic. So this is where there's like a nice equilibrium over here of what we're saying when we're talking about pH is how much hydrogen is just available in a solution. And hydrogen, you'll see it with like a hydrogen plus on it because it's just the hydrogen, it's just the proton, it's not with an electron. Oh, I think I might not have put a periodic table in these slides. So hydrogen is the smallest atom that we have. And being so small, it can make bonds and leave bonds a lot easier than other bonds to molecules. And so since it's so small and it can leave without necessarily taking an electron with it, it's just kind of available in water. I'll explain that a little bit more later. But so the counter to a hydrogen atom just floating around in water, the counter to it is an OH negative. And so when you get these two together, it's neutral. Nothing's really happening. They're not, hydrogens aren't really moving around too much, and OHs aren't stealing hydrogens too terrible much. It gets complicated, and giving this talk, I was like, do I talk about this first or that first? And I'll try to tie up all the loose ends. If I say something that doesn't quite make sense, like the nature of a hydrogen, I'll try to come back to it. So what's a mole? This was invented by Avogadro I didn't even say what year it was, but basically a mole is 6.022 times 10 to the 23 is a mole. It's just kind of an arbitrary number. It's like, but it makes sense how they came up with it. It's like saying, if you're dealing with peanuts, you're a peanut farmer, and everybody just agrees that a box there's a couple different ways to come at it. Like, oh, a case of peanuts is 20 pounds. Or you could look at it like a case of peanuts is 6.022 times 10 to the 23rd peanuts. I mean, that'd be a lot of peanuts, but it's just a unit that everybody has just agreed on. Okay, that's what a mole is. It's exactly this many atoms. And so that's also where, if you look at a periodic table and you see the molar mass, it's basically how much does a mole of this weigh? So we use moles in a lot of different ways. And stoichiometry is a really important one, where stoichiometry is basically converting and matching up atoms. So we all know that water is H2O. So if you were going to say react water with some other compound and say that compound's like, all right, just off the top of my head, like C3H10N2 or something like that, where you can't say a pound of water or a liter of water, kilogram of water, and a kilogram of whatever you're going to react it to are going to react, and there's not going to be any leftover water. Like, you actually have to break things down into moles to get, so like over here, 100 grams of carbon dioxide is 0.2 pol. So carbon this is the molar mass. You can find that on a periodic table. So as carbon, oxygen, so 1 carbon atom, 2 oxygen atoms. So then you have to break it down to get that CO2 is 44 grams per mole. Then you just take that times 0.02. So I bring this up because understanding what molarity is important to a lot of chemistry stuff and some of the stuff we're going to be talking about. So yeah, like hydrogen's this tiny little atom, and it doesn't absolutely need to have an electron with it. So what I'm pointing out here is that, you know, this hydrogen can react to oxygen and turn ethanol into acetaldehyde. There is a catalyst involved here. We'll get into catalysts a little bit later, but you can see that it's changing just this one little, and not to get too terribly into it, but when you see drawings, stick drawings like this, if you're not used to it, there's a carbon here, there's a carbon here, and it doesn't have it, but there's like 2 hydrogens, 1 on either side here, 3 hydrogens over here. Hydrogens are, it's funny how they're so important to chemistry, but they're so overlooked. Like, you don't even see them on the drawing because people just take it for granted that there's hydrogens there. Otherwise, if there's not a hydrogen here, so there's like 1 hydrogen sticking off this spot, the other electrical bond is with that oxygen right there. So it can actually change conformation of compounds. Like, so like, here's some fatty acids. Fatty acids are important because like phospholipids like this, and they did draw the hydrogen on here, which is nice. Sometimes you'll just see this as like the head, this unit here, and it'll just be kinked carbons. They won't even draw the hydrogens on there. But this is a important compound because like lipids like this are what are in phospholipid bilayers. This is what makes up all of our cells. This is the thing that keeps the outside of the cell outside and the inside of the cell inside. And just a removal of one of these little hydrogens right here is making this double bond right here. And it changes the conformation of this entire molecule. So that instead of like straight molecules like this, they have room. And this is the difference between fluid, like something being fluid and something being like solid or viscous in this case. So just even the addition or subtraction of this tiny little hydrogen, people even call them protons at some point. They'll be like, oh, a proton moving here and here. They really mean a hydrogen. I don't know. They just don't want to pronounce hydrogen or not. One kind of weird aspect to pH and the availability of hydrogens just laying around in solution is different compounds. You can actually predict at what pH a hydrogen is going to pop off. So like, so with these back here, you can actually predict with this chain what hydrogen is going to pop off and at what pH it has to pop off. So pKa value starts dealing with like when a molecule like carboxylic acid here, when it turns to this. And so around 5 is when it, I mean, these numbers are, I can't get into the math here, but you can accurately predict when complicated molecules will lose a hydrogen and then what conformation it'll take. And it all has to do with how electrons move in here, like some bonds are stronger than others because there's more, the electron field is just stronger. It's just a better connection. Where whenever there's like an oxygen and a hydrogen, like that's a really weak bond because there's so much electrical, so many electrons around a hydrogen that they're around an oxygen, that this hydrogen doesn't really feel that great of a connection. And it's like, so something like this compound, that either this hydrogen or that hydrogen is going to pop off pretty quick. Where if you have a lipid like this, these hydrogens are pretty happy being where they're at. It's a lot tougher to pop them off. But if you pull a hydrogen off of this, it will change in conformation. I guess that's the whole point that I'm trying to get at there. So another interesting thing about molecules losing a hydrogen, and molecules will lose a hydrogen if there's, or will gain a hydrogen or lose a hydrogen, just depending on what's around. So if we have an acid and a base, and it goes through this chemical reaction where this water, which is acting as an acid, water can act as an acid or a base depending on the conditions. So this water just lost a hydrogen and now it's OH negative. That's going to go somewhere else and like pull a hydrogen. If in the right conditions, that'll pull another hydrogen off, because things don't want to have a negative or positive charge on them. They want to be completely neutral, but some situations they just can't, like acidic or basic. So in this reaction, this counts as a base, this counts as an acid. And then once you have a reaction, then you have what we call like a conjugate acid or a conjugate base. And so the more, let's see if I have, what's my next slide? Yeah. So the more you have this reaction happen, like you have a reaction that's constantly happen, there starts to get this buildup of conjugate acids and conjugate bases, and that produces what we like to call a buffer range. So if you look at, let's look at this example. If you're adding acid to, so if we're trying to increase the pH in this, and we have a buffer range, and this buffer range is because there's conjugate acids and there's acids and conjugate bases in a solution together. So like right around here, you're adding like, if to go from like 0.0 to 0.1, like if you just add this much, like it's pretty significant change in pH. You get all the way up to 1. You add a half, and like right around here, the more acid you add, it's not changing anything as much. Like you just have to, so when I did my internship at Miller, I did a lot of work with enzymes. And part of the work with enzymes, I had to figure out, we had like this particular mash, and it was like, barley and some oats and, just regular beer stuff that you throw in there. I had to figure out exactly where the buffer range is, because we had an enzyme that worked at a very specific pH, and we had to figure out where that pH was and how much acid we had to add to get to it, but also how much was way too much. So if I had an enzyme that only liked to be like at 3, and we had these are all really low numbers, but if it was something that we had to have at like 3.2, and we're adding acid, like whoever's doing the brewing is just adding acid, and they're like, man, I already added like 200 milliliters, and it's just not changing. We need to know if that's in a buffer range that they're in, because, they add like 20 more milliliters and they're all of a sudden they're at pH 4 or 5 or 2 points higher than they need to be. That's a big problem. And I think Joe's going to get into more buffer ranges and what they need as well. So So now that I talked about enzymes a little bit, we're just going to talk about enzymes. So first we have to talk about proteins. Proteins are just chains of amino acids, just these little units. But the way that you that like humans or any living organism, plants do this, animals do this, microbes do this, they all make proteins. And proteins are amazingly versatile things. Like they make, they do structure, they do, like if you need a tiny little machine that does anything, if you need a muscle to move, it's a protein. If you need something in the phospholipid bilayer to like bring anything into the cell, that's a way to do it. So basically think of proteins as like tiny little machines. So here's the protein structure. It's amino acids. This is another way just to look at it, where it's like just a chain of these amino acids that have different properties and different things, so that there's the primary, secondary structure is just like, okay, how they're shaping in regards to each other. And there's a lot of things like bonds, a lot of different kinds of bonds that happen. Because all these different kinds of bonds happen, then you get a tertiary structure that's all the polypeptide chains. And then you get a bunch of like some of these together, and that's a quaternary structure. And that's basically what a protein is when we're talking about the quaternary structure. So maybe I should stop and are there any questions? Can you guys hear me? Am I still hooked up to the internet? I heard a chuckle.
Yep, you're all good.
Yes,
No, you're good.
Okay, all right. Is anybody falling asleep yet?
No, I great job on the visuals. This is fantastic.
Oh, good. Okay, great. Okay, so this is what a protein is this. It has so many uses, and it's so biologically important. They're really, really neat. So an enzyme is just a protein, and an enzyme just basically acts as a catalyst for chemical reactions inside any living thing's structure. And it really makes it so that a lot of functions can happen. And by definition, a catalyst, it's not used up, it's not part of a chemical equation. I mean, it's part of a chemical equation because you take it into consideration, but it doesn't get used up. It just totally just makes this reaction happen. And so like, here's a good example of like just these two compounds that come in and either get like snapped together or pulled apart. We're all familiar with alpha and beta amylase. I won't get too much into that, but it's just these enzymes just basically make it so that this reaction can happen without whatever reaction it is, without a ton of energy going into it. So when we're talking about acids and bases, like basically something that's basic, like a molecule that you could consider basic, is just a molecule that has like a hydrogen or a couple hydrogens missing. So they're just trying to pull hydrogens off of anything they can find, and it doesn't matter if it was already attached to something. And if there's if something like OH positive runs across something that that just has a really weak hydrogen bond, like some alcohol, it'll just pull that hydrogen right off and keep it. So like I said before about how it'll change, a missing hydrogen can change the structure of something. When you get, this is why proteins and enzymes, pH is so important to them, is because if you, I should back up to this. So this enzyme right here, I'm not even sure what enzyme this is. It has what we like to call active sites, like right here and right here. And it's usually very, very, very specific. Like it has to fit, like these two compounds have to fit perfectly in here to like be assembled. Likewise, if it's an enzyme that like pulls apart stuff, like amylase, that enzyme has to be in a perfect shape. Otherwise, it's just not, those active sites are pulled apart. It's like, all four wheels of your car have to be touching the ground. Because if you've got 2 wheels on the ground and then 2 wheels up in the air, it's not going anywhere. It's just in the wrong conformation. So you can see here where like a folded protein, you pull enough hydrogens off of it, whole thing just unravels. And so that's also how caustic works. Caustic is just a super high pH, very basic compound that just goes in and just rips hydrogens off whatever it finds. So this is how we clean our equipment. We get proteins off, but it doesn't just pull up hydrogens off proteins, it pulls hydrogens off anything it finds. Your skin, your hair, whatever. Here's another technical representation of a enzyme. And I just put this up here because they are so incredibly complex. Like sometimes it's amazing that anybody's alive, I'll be honest. But like stuff like this is just super common every day. Like, and we're still learning about it. We really are. And so this is just really complicated, technical, but look how complicated, like you just pull a couple hydrogens off here or there. This active site right here is just nothing. It's just a mess. And then all of a sudden, you know, oh, why aren't my starches converting to sugars? Because the pH was wrong for this enzyme to be active. Now, luckily, stuff like amylase has a pretty great pH range. And I know we talk about temperature ranges with that as well. That also has to do with its conformation, its shape, and if those active sites can actually be active. Oh, here we go, right there. So starch, of course, is made out of amylopectin and amylose. And yeah, I just put this up here just so this kind of looks, you know, it just kind of demonstrates where, you know, how complicated this thing is that we're expecting these enzymes to work with. Amylopectin's a little bit more tough to deal with than the amylose, but it gets them all. Yeah. Okay, also, pH has to do with inhibited microbial growth. Some microbes do not like acidic conditions, and some are great with acidic conditions. It's like you can see over here, lactobacillus. Lactobacillus will go to, I think we talked about the magic sweet spot in food science was 3.6, is where under that, it was either, actually, Erica Gonzalez, is it 3.4 or 3.6 where you don't expect any other kind of fungus or any microbial growth? Do you remember?
Can you hear me?
I can hear you right now.
Oh, okay, this does work. It's roughly that. I don't remember right off the top of my head. I'm also just really tired.
Okay, no problem.
But
So,
you're about there.
yeah, it's 3.6 or 3.4. I think it's 3.6. Anyway, so yeah, this is just kind of demonstrate that, like, you know, we expect a whole lot of pH or a whole lot out of pH when we're making beer, and sometimes it's not super common. But also, yeah, pH we use it to. Now, I hope nobody's making beer that's around 3.6, but you can also kind of see that, like, you know, if you've got a, you know, something around here, you can. Now, this, of course, is not a comprehensive list of all the microbes that, you know, could infect beer, but just a little demonstration of, you know, different things like to grow in different environments, and pH is a big factor.
I used to work at Octopi. All the beers 3.6.
And it all tastes like strawberry and Oreos.
He's right.
Anyway, so just to wrap it up, there's other aspects to consider when you're dealing with pH. Taste is a big one. Hop utilization is also something to take into consideration. Water treatment's a big thing to take into consideration. Just like I said, you know, those if there's a bunch of hydrogen around or a bunch of like OH all over the place, it will change your chemical chemistry, and it'll take like scaling, you know, just a little bit of lactic acid or muriatic acid can make a big difference of if you have like a ton of scaling that you're pulling out of your hot liquor tank every other month versus, you know, no problems at all, and even that much less that you have to use in your kettle. I think that's about what I've got. I know there's a lot, and there was a lot more that I could get into, but I feel like I was already kind of going for a while. So does anybody got any questions? Okay, I'm hearing no. Okay, I will.
You said you got more you can go into. You wanna keep going? I'm enjoying this.
Well, what kind of questions you got? Lead me down the primrose path.
No,
there.
I just want you to keep. This is awesome. Like this is
Patrick
a
wants
very
you to talk
great
about
thing here.
salts. Let's admit
No,
it.
I'm not going to talk about salt. Patrick, when are you going to give a talk about salt?
Joe's already got a better one.
Mm-hmm.
I'm not talking
Well,
about salts today either.
I ferment a lot of stuff, and I was talking to a friend of mine that was making a pepper ferment, and he was questioning what he should do for it. You know, it's a lacto fermentation, and in that community, anything under 4.6 pH can be water bathed instead of pressure can for preservation if you choose to do that. And so he sent me over some. It was what are those jalapenos that are smoked in that adobe sauce, whatever those are called. Well, he did that, and it was at 3.53 was what that ended up at. I'd also brew kombucha, and I bottle it when it's at 2.85. So something makes it get that low in kombucha. The way it works is when you put that sweet tea in with your starter, it's at a certain pH. I've never measured mine. I only measure the finished product. And so the yeast takes over it first and causes, alcohol. And then the microbes come in and eat that alcohol, and they lower the pH, put the yeast to sleep. Then another microbe comes in, lowers the pH some more, puts that microbe to sleep. It becomes anaerobic because of the pellicle that forms. And at 3 what did she say? 3.5 or 3.6? Something takes it down to 2.85.
There could.
I would love for you to graph that as you went and talk about that later. I'm really interested in that.
See, the similar thing happens in kimchi manufacturing, where you have Lucanox stock takes over first, but you're also using salt as an inhibitor. They're using osmotic pressure to push some other microbes out. So Lucanox stock's the first one that moves into there, and then it goes lactobacillus after that. And lactobacillus can get pretty low, like that's one of the lower ones you can get. But there might be some other chemical reaction that's not biological after that. It might get it down to like 3.2 or something, and then there might be some other chemical. I'm not sure how capsaicin works with the rest of its environment. I haven't messed around with that too much.
Yeah, I don't need. All I know is it tastes really good. You know what I mean? It's got a really good flavor, and it doesn't get moldy. It's in. It's not treated with anything. It's not pasteurized. We don't water bath anything. We just keep it in the refrigerator as a live. It's a live ferment, so it's got all that good stuff like kefir and yogurt and sauerkraut, and it doesn't never get any mold or anything. It never lasts more than a year, though.
Joe, I just noticed how professional you're being that you're wearing an octopi shirt.
Yep.
Trying
to keep it classy today.
Yeah.
All right. So should I
You want to take over?
Yeah. Let me get my screen all shared up here. All right. What in the heck is that showing? It took it to the end of the slideshow. Ooh. Let's try that again. All right. All right. So what I'm going to focus on here is really taking what Matt laid the foundation of and sort of apply it mostly to brew house operations, because that's really the control point for making beer. Most of this happens in the brew house, and so we want to think about pHs. We want to think about why we're controlling it, And first question really is just why? Why do we care? Why put the effort forth to to do something if it doesn't matter? In this case, it does matter. We want to get the pH in the right range for our mash enzymes to work, primarily the amylase enzymes for degrading starch, but also to some extent, and depending on the kinds of beer you're making, the peptidases that break down proteins as well. We want to keep our pHs low during sparging to minimize tannin extraction. We want to keep them reasonably low in the kettle to prevent excessive wort darkening, harsh hop bitterness, loose tube piles, and we also want to make life easy for our yeast. So, excuse me, keeping those pHs as low as possible is going to help out with this. This slideshow seems to be moving itself, even though I'm not in a slideshow. Okay, so so we want to address pH at various points throughout brewhouse operations here, and so the first thing we want to look at is our water and how that's impacting the processes. So the main contributing factors in the water are its alkalinity, which is really a quantification of its resistance to acidification. So alkalinity is just the amount of acid that it takes to lower a sample of a solution to a pH of 4.3 or 4.5. Different people do it different ways. For what it's worth, I use 4.3. It doesn't make that big of a difference. If you're going to get something down to 4.5, it doesn't take much more to get to 4.3. So it's kind of in the wash. It's just which number you plug it into your calculations. Hardness is the combined concentration of calcium and magnesium ions. And those they lower pH. That's not really their primary purpose. Magnesium is very important for yeast metabolism. Calcium is important for things like calcium oxalate precipitation and protecting enzymes, yeast flocculation, things like that. But they do lower pH. They're not quite as effective at doing so as alkalinity is at raising it, but they need to be considered. So before we really get into quantifying these numbers, I want to talk a little bit about the units of water chemistry. So if you're looking at a water report, you are going to see a lot of units reported as milligrams per liter or parts per million. And as far as brewing is concerned, they're the same thing. You can use those interchangeably. But if you're going to do math for calculating things like acid additions and pH changes, it's nice to convert those to a charge-based unit, such as milliequivalent per liter. And milliequivalent per liter is just the ionic concentration multiplied by the charge, the ionic charge of each molecule, divided by its molar mass. And then there's this monstrosity known as milligrams per liter as calcium carbonate, or parts per million as calcium carbonate. A lot of water reports will use that for alkalinity and total hardness, and sometimes they'll use it without even telling you. It might just say parts per million, but if you see like 300 alkalinity, it's not a straight parts per million number. It's this charge-based unit. And so all that really is if you have your milliequivalents per liter, multiply it by 50. That's how you get to parts per million as calcium carbonate. So because alkalinity raises pH and because calcium and magnesium lower it, back in, I believe it was 1953, a German brewing scientist named Paul Kolbach did some research and determined that 3.5 milliequivalents of calcium or 7 milliequivalents of magnesium is enough to neutralize 1 milliequivalent of alkalinity. So he came up with this concept of residual alkalinity, and this is driving me nuts. I don't know why these slides are auto-advancing. I'm going to stop this for 1 second. Sorry about that.
You might have an auto timer on in your PowerPoint program. I don't know how to turn it off, but I know it exists somewhere.
Sure. Yeah, it's interesting because I'm not actually in a slideshow. So I'm going to escape out of this. Like all I did was go into here and turn it onto the reading view, which makes it look like a slide. So if I go to slideshow here, timings.
So while Joe's figuring that out, I thought of a couple things that I wanted to say about my presentation.
Good timing.
Fill a little time here. Yeah, Joe just mentioned pentase. In case everybody's not familiar, when you hear the suffix ASE, it's almost always an enzyme. Amylase, pentase, protease. Yeah, and then I'm not sure if I drove the point home that like the pH scale is a log 10 scale. So the more you get away from 7, the harder it is. And it's just like, so if you added, like, let's say you had a bucket of water and you were adding an acid to it, and, you know, 10 milliliters changed it 1 pH, like up to, you know, down to 6 pH, then it'd take like 100 milliliters to get it down to the next one, and 1,000 after that, and et cetera. So it's a log scale. So when you see 3.2, like that's really acidic. It's not like the difference between 3.2 isn't the same as the difference, you know, the difference between 3.2 and 3 isn't the same as the difference between like 7.2 and 7. Does that make sense? Not sure if I was clear about that. All right. Thank you, Joe.
All right, I think I'm back in action here. If it keeps doing it, I'll just deal with it. So this residual alkalinity is a good way to quantify the overall impact of the hardness and alkalinity of your water. One thing to note, if you read some of the literature about cold box studies and residual alkalinity, sometimes they attach a pH shift to it. They'll say, oh, you know, 1 unit of residual alkalinity will shift your pH this much. And that is something that Kolbach studied, but he did that on wort and not mashes. So taking this and applying it to mashes is not necessarily valid. And finally, for this residual alkalinity, you can use any unit for all 3 of these components. They just all have to be the same, and it has to be something charge-based. So it has to be a unit that counts the number of ionic charges, not the number of molecules or weights or anything like that. So in general, you want to remove alkalinity. Some people are lucky and get to brew with naturally beautiful water that doesn't have much alkalinity, but a lot of us have to deal with too much of it. So we need to have ways to remove it. And that's going to result in lower pHs throughout your brew house processes. And it really starts with the mash. If you get your mash pH right, it's going to set the stage for everything else downstream. It doesn't, what you do in the brew house, it does influence how your yeast is going to start fermentation. But once fermentation is going, your alkalinity, your water is kind of lost in the mix. It's not really that big of an influence because those organic acids produced by the yeast just dominate and pretty much take the beer where it's going to go. So if you have to remove alkalinity from your water, a typical target is around 1 milliequivalent per liter, or 50 milligrams per liter is calcium carbonate. So there are a number of ways you can do that. One way that is not very common is lime softening. That is where you add calcium hydroxide to your water. And what that basically does is it combines with calcium and bicarbonate in your water and drops out calcium carbonate. So it drops chalk. And that will, as long as there's enough calcium, you can get your water down to about 0.5 milliequivalent per liter of alkalinity, but it does drop this solid chalk. So if you're going to look into lime softening, you're going to need to come up with a way to remove it. Lime softening, and I kind of wish Gary was still on because he could correct me if I'm wrong, but I'm pretty sure lime softening is Ryan-Heiskebo compliant because it doesn't actually go into solution, it just pulls stuff out. He could correct me if I'm wrong on that, but I think this was a workaround in kind of old German brewing that's not really as common anymore. Reverse osmosis is what a lot of people are doing these days, and that pretty much strips everything out of your water. It's creating water that's fairly close to distilled water. It does come at a couple of costs. It generates a lot of wastewater. Although the manufacturers are getting better at that, it's becoming less and less. And the water itself is also corrosive. So you don't want to take straight reverse osmosis water and put it in your stainless tank. Some types of stainless and grades of stainless are more resistant to it, but in general, reverse osmosis water, because it has so little in it, it wants to strip things out of the compounds it's in contact with. So a fairly common practice, and this is what we do at Octopi, is we blend back in a certain amount of city water to give it some mineral content, so that it's not corrosive. Nanofiltration is pretty similar to reverse osmosis, just not quite as small of membranes. So instead of taking just about everything out, it takes out approximately 80% of monovalent ions, which means it has charges of positive or negative 1, like sodium or chloride. And it takes out divalent ions, which would be calcium, magnesium, carbonate, if it's at the right pH at higher rates. So nanofiltration is still pretty good at reducing hardness and alkalinity, doesn't waste quite as much water, and doesn't quite corrode as badly as reverse osmosis. So I'm kind of surprised I don't see it more often in breweries, because it should be cheaper than reverse osmosis, because it doesn't have to be manufactured to as tight of tolerances. And I know you can get units from companies such as GEA, where the outside, the housings are all the same, and it's just which membranes you put in it determine whether it's reverse osmosis or nanofiltration. So, you know, maybe people are just thinking, oh, what the heck, I'll just do RO because I've already got all the gear for it. But then more often than not, you're taking stuff out of your water to add it back in. So that's why you see some breweries, and those of you in Madison, Giant Jones is a good example of this. They have plastic holding tanks for the water because RO is corrosive. But you still have to heat that water, and that typically is going to happen in a stainless tank. So you got to be aware of that potential. The last way I wanted to talk about to remove alkalinity is acid additions. So if you want to neutralize a given amount of alkalinity in, let's call it milliequivalents or milliequivalents per liter, what you want to do is take an acid and add an acid in an amount such that its dissociated hydrogen ions match that milliequivalent drop that you want to achieve. So dissociated acid, like Matt said, it's acid molecules that are separated into hydrogen ions and conjugate bases. And as far as we're concerned, like dilute chemistry and what's happening in breweries, strong acids release all their hydrogen ions. So we would call that 100% dissociation. So there's really no change. You're going to add this and it's going to get rid of all its hydrogen ions. Weak acids, that is not the case. And how much of a weak acid dissociates depends on the solution pH. And as your pH goes down, your dissociation decreases. So basically with acids, that's a diminishing return. You're going to add a little bit of acid and maybe your pH is still high, and that acid likes to release a lot of protons. But as you progressively add more and more acid, it gets less efficient. And so each molecule, or the collection of molecules, like collectively release a lower percentage of those hydrogen ions. Kind of similar to hop utilization, in that you keep adding more hops, you get less and less as you add more. So a similar concept here. So to try to figure out weak acid dissociation, you start with these pKa numbers that Matt was talking about. And Matt, you can correct me if I'm wrong, but I'm pretty sure the pKa is the pH at which an acid is 50% dissociated, I think.
That is correct.
Okay. And so you can take that pKa and put it in with an equation. Now, can you guys see my cursor on here?
Yes.
All right, good. So you probably just see me just being completely ADD this whole presentation and just kind of going everywhere with it. But
Yes.
You've got the pH right here. And so if you know your solution pH and you have your pKa from the acid that you're using, you can figure out how much of that is going to be dissociated. And so if you're using, again, a strong acid, that number is 1. So this is a fraction and not a percentage. So a few of the acids that you could use to reduce your alkalinity. I got a couple of strong acids here, and this isn't really very common because these acids are dangerous to handle. And especially in the case of sulfuric, even potentially dangerous to breathe if you're like around those acids. So pretty hazardous stuff. I do know Capital Brewery was using hydrochloric acid, which is also known as muriatic. I don't know if they're still doing that.
I can tell you that they're not.
Oh, they're not. Okay. All right,
Yeah,
interesting.
that changed while I was there because Myriad, literally it was by the loading dock and it was corroding the metal.
Sure. Oh yeah, I remember
the
seeing
air.
that teaching the.
Yeah, they're
MIT
using lactic now.
All right. And so I've got just a couple of figures here, and this is really more for reference. If you're gonna find this presentation later or ask me for this information, I'm happy to dig it up and get it to you. But basically, if you want to neutralize a milliequivalent of alkalinity, you need 36.46 milligrams of pure hydrochloric acid. So sulfuric, even though sulfuric has one more hydrogen ion per molecule, it can release two. This is a much heavier molecule. So those two hydrogens don't do quite as much in the grand scheme of things because it's so heavy. So you actually need more sulfuric acid than hydrochloric to neutralize the same amount of alkalinity. And I put these other notes in here because if you're going to use hydrochloric, you're also adding chloride. If you're going to use sulfuric, you're adding sulfate ions. So you're changing your water chemistry in those ways as well. Phosphoric acid is a weak acid, and it's got 3 hydrogen ions that can be released. So it has 3 separate pKa values. And so each of those hydrogen ions behaves in its own way as pH decreases. And so if you're at a pH of 5.3, which is a pretty common MASH pH target, phosphoric acid to neutralize that 1 milliequivalent of alkalinity, you're going to need about 97 milligrams. So about twice as much acid as you would need for sulfuric. Flavor impact of phosphoric is minimal because it's basically contributing phosphates, and that's what your malt contributes. So phosphoric acid is attractive for that reason. But for treating water, it can be tricky because if your water has a lot of temporary hardness or a lot of alkalinity, you can drop calcium phosphate. So I guess temporary hardness would be the thing that contributes that calcium. And those calcium phosphates basically behave like chalk. So my first brewing job, I worked at JT Whitney's, which is now Vintage on the west side of Madison. And we treated our water with phosphoric acid, and there was just layers of built up white solids in the hot liquor tank that occasionally needed to be scraped out and run strong acid cycles and things like that, basically try to passivate your tank with a layer of stuff on it. So yeah, it can be troublesome. I know if you read the water book by the Brewing Association, there's a whole lot of kind of debate about how much of an impact this really is. And I can tell you, at least for Madison water, it's a huge impact. Now, if you're brewing somewhere else that doesn't quite have the alkalinity that we do or the hardness that we do, then maybe it's a non-factor. So it really is situational. But as far as brewing in Madison, I wouldn't recommend treating your water with phosphoric acid. Lactic acid is really my go-to because it's also a weak acid. And you can see that it's got 6 hydrogen ions in there, but it only releases 1. So it's only got one pKa value. At MASH pHs, it's approximately as strong as phosphoric, but it doesn't precipitate solid. So you can add this to your water and just clear out that carbonate alkalinity and not worry about having to separate out from a mess. The potential downside of lactic acid is that its byproduct is a lactate ion. And there really is not any broad consensus on how that impacts the flavor of beer. There have been a couple studies that were inconclusive, where people, to varying degrees and not with any statistical significance, have said they could or couldn't taste a difference. For what it's worth, when I was working at Ale Asylum, I was working there when we built the new facility, and I brought up doing lactic acid for water treatments, which they hadn't done before. And I thought it was going to be a deal breaker because they were very Reinheitsgebot minded. But when I kind of explained the process and the benefits, Dean was all about it. And as a trial, I brewed a Pilsner at home. So to take a light beer style that requires a lot of treatment and over treated it with lactic acid, and the beer was delicious. So we decided that was a go ahead. Acidification by sourwort or acidulated malt, other common practices in Germany to get around Reinheitsgebot are also relying primarily on lactic acid, just from natural biological souring. So there's also a pretty rich history of doing that to justify why lactic acid is okay. but you know, everybody has different philosophies, and as far as, you know, what you want in your beer, what could potentially, even if something, you know, if I don't find it offensive, somebody else might. So that needs to be considered when you're thinking about a lactic acid treatment. So I know it's fairly common practice for breweries to acidify to a target pH, and that's generally not a good idea. I've seen this happen in several different situations, and it's when I test it now, it's pretty reliable. But if you treat your water with an acid, it's going to drop to a certain pH level, and as long as it's not so low that the acid dominates all the carbonates in there, basically, if it's treated properly, you're going to get a pH that might get down into the mid 5s. But you take that water and agitate it, and CO2 will escape, and the carbonates in that water that are remaining will rebalance. And it's a pretty slow process. But if you're willing to put, you know, a sample of treated water on a stir plate for 15 minutes and just vigorously stir it while you're measuring pH, you'll watch it over the course of that 15 minutes climb all the way back up to close to what it started with before you treated it. So in the case of Octopi and Ale Asylum and Capital is actually where I first noticed this, climbing all the way back up to 7.5. And that water, once it gets up to 7.5, is going to behave in the brew house pretty much exactly like it would behave if it was at 5.5. So the alkalinity is still the same. It just has a different pH. So the pH doesn't become it's not very meaningful unless you know how much of that CO2 you've driven out. And unless you've driven out none of it or you've driven out all of it, you don't know how much CO2 you've driven out. So it's really just a arbitrary value at that point. So if you're relying on acidifying your water to a target pH, if that CO2 removal isn't consistent, then you could be getting unpredictable alkalinity from that process. So alkalinity is really what determines how your water behaves in the brew house. You might as well just treat it to a certain alkalinity instead of introducing this kind of intermediate pH value. So treating water to a given alkalinity is easy with strong acids, but when you're dealing with weak acids like lactic and phosphoric, you've got this variable dissociation. So if you're working in brew house pHs, you know, mid 5s, low to mid 5s, lactic and phosphoric acids are both like above 95% dissociated. So they're mostly behaving like strong acids. But if you're going to do a titration and figure out the alkalinity of your water that's treated with that acid, that variable dissociation has a huge impact. So at 4.3, I think lactic acid is like 50-some% dissociated. So Madison water, for example, if we call this water 6 milliequivalents per liter of alkalinity and I treat it to 1, if I do an alkalinity titration on that, its actual alkalinity is going to be somewhere around 2.3 or so, because that lactic acid actually acts like a base at that point and pulls out hydrogen ions from the alkalinity titration. So effective alkalinity is kind of a nice way of making sure brewers speak the same language. And that's just the alkalinity that the water would have if it was treated with a strong acid instead of a weak acid. And that's a really good predictor of chalk precipitation and brew house performance. And for effective alkalinity, you just use the same target. You use 1, typically 1 milliequivalent per liter. So I'm just going to give an example because it's kind of a weird concept and it might not make any sense, but the numbers will help. So if you look at this and it's got, clicking the mouse moves it. If you got water that starts with 6 and you want to take it down to 1, then you're going to add 5 milliequivalents per liter of acid. And so in the case of lactic, it would be that many dissociated hydrogen ions. So it's actually your effective alkalinity that is the 6 minus 5 = 1. It's the true alkalinity that varies, where you get this 2.3 number because it takes so much more acid to get it down to a pH of 4.6. So if you're thinking in terms of how much alkalinity you want to remove instead of what you end up with, that's how you get to effective alkalinity. So you want to remove 5, what's left is your effective alkalinity. So I tend to think of things in those terms. So we've talked about neutralizing alkalinity for the sake of not having your water raise pHs throughout the brew house. Now I want to talk specifically about the mash and where we want to be and what's going to affect that. So if you were to take pale colored malts and mash them with distilled water, let them go through their starch conversion, cool those samples to room temperature, you're going to end up typically with a pH around 5.6 to 5.8. But if your grist includes dark grains, your pH is going to be lower. If your mash water is alkaline, your pH is going to be higher. And if you have a lot of calcium and magnesium, your pH is going to be lower. So all those things are contributing factors to your mash pH. Where that mash pH should be, there's no exact consensus. Different brewing scientists think different things, but they're all the same general ballpark. Bamforth is saying 5.3 to 5.8, maximize extract, lower values are better for protein breakdown, and saying that most mashes are 5.3 to 5.5. Coons and Narcissus calling for a little bit lower numbers, 5.5 for starch conversion, 5.2 to 5.4 are ideal for beer flavor and stability. I typically like to aim for 5.2 to 5.5. And so if I'm plugging it into a calculator, I'll do 5.35 because it's halfway in between. Some people shoot 5.2 to 5.4. That's a good pH range. So typically low to mid fives are what you're looking at for a mash pH. And again, that's samples cooled to room temperature. That's important. So all the pHs that I put in here are assuming you're going to cool that sample to room temperature, because the pH itself decreases as temperature increases. And if you're going to stick a pH meter in your hot mash, you're going to burn out that pH meter really quickly. And historically, where a lot of these pH figures came from, portable lab equipment didn't exist. You had to collect a sample from the brew house and get it back to this equipment that took a while to get started. And yeah, it was probably closer to cold than warm by the time it was measured. So mash pH tends to reach equilibrium pretty slowly. And this is where I'm probably kind of a little bit of a contrarian, because a lot of people talk about measuring pH, give it 5 minutes and measure it, or give it 15 minutes and measure it. I like to wait till the end because I know what I'm getting. And because I'll know it's at equilibrium. The downside to that is you can't make changes on the fly. But I really question that methodology anyway, because to adjust mash pH on the fly when it's not necessarily at equilibrium, it's very easy to overcompensate, and your mixing is not always great. So, you could be doing more harm than good if you're trying to adjust pH on the fly. If you do the math right up front, you're going to be close, and measuring it at the end is going to give you a feedback loop to dial it in on future batches and refine your processes. So I like to sample at the end of starch conversion. And if you can get it from the mash mixer, great. Sometimes that's not easy to do, depending on your brew house configuration. So if you have to, another good way to do it is to take your first running's wort at its peak extract. So kind of wait till your foundation water works its way through both the Vorlauf and the startable water, and then sometime before adding your sparge water, get that pH sample and get your reading. And again, I'll say it for probably the third or fourth time, cool that sample to room temperature before you measure it. In terms of what you use for a pH meter, automatic temperature compensation is important, but it only solves half the problem. It basically corrects the meter's response to temperature, but not the mash's response to temperature. So the mash, its pH is physically also changing with temperature, and the pH meter doesn't account for that. So I threw an equation in here that you can use to estimate the difference. I recommend only using this correction for fairly small changes. If you can't get your mash to 68, but you can get it to the 70s, like that's probably fine. But the farther away you get, the more impact this calculation is going to have in terms of it just being a ballpark measurement. I mean, you can get malt, the same type of malt from the same manufacturer, different lot numbers are going to have different pH shifts. So you really only want to use this for small deviations from your ideal sample temperature. And then pH meters, if you've never taken care of a pH meter before, it can be kind of a steep learning curve. in terms of how often it needs to be calibrated, which is pretty much all the time. We do it every day at Octopi. Every morning we calibrate the pH meters. If you don't use it quite that much, you could probably get away with doing it weekly. You also have to make sure that pH meter is being stored correctly, because if that electrode dries out, that's going to be a lot more expensive to replace than the storage solution that would have kept it in working order. So in terms of predicting mash pH, you've got all these factors that go into it. And what you want to do is look at each component and say, how much acid does it take to move this component to your target pH? So acid required, I tend to say acid, and what I really mean is dissociated hydrogen ions. But if that value is positive, you need to add acid. If that value is negative, you need to add some sort of a base to bring that pH up. And so your components are really your water, and your components of the water are going to be the alkalinity, the calcium, the magnesium. So you can take kind of known calculations and apply that to water. So things like residual alkalinity and carbonate distribution. But for grain, it's trickier. Grain is really kind of the Wild West because it hasn't been studied that much. And so to estimate grain acid requirements really requires testing. And so I've started to do that over the last several years. I started doing this at Ale Asylum, and I've continued doing it at Octopi, where I'll take a given grain and I'll make 4 sample mashes from it with distilled water and varying amounts of either sulfuric acid or sodium hydroxide. And so I'll add known quantities, mix them together, basically conduct a mini mash at starch conversion temperature, cool it down, and then measure the pH of those samples. And so I can use those results to quantify grain acid requirements. So I've got a few charts here I'm going to show you. This first one is base malts. So I've got several different base malts here, some Pilsner, some two-row brewers, Vienna, Munich, wheat and spalt are also in here as well. So you can see that basically as you get darker in color, these lines get farther down on the chart. So that means or you can think of them as moving down or moving to the left. So these are working at lower pHs. So the darker you go, the more acid is being contributed. These 2 lines with the shallower slope, those are wheat and spelt. So you can see that this 0 line here is distilled water pH. So wheat and spelt start at higher pHs than these other base malts. But as you add acid, it doesn't take as much to move them from one point to another. So they start at higher pH, but they have less buffering power. And it's nice to know that wheat and spelt pretty much behave the same. So if you know how wheat's going to work, you can apply that to spelt if you're making beers for people that want to do that. Patrick's laughing. So here I've got some mid-color malts, so some high kiln malts, some caramel malts. You know, I don't even know why it says high kiln, because I did have some at Ale Asylum, but these are Octopi numbers, and these are all caramel malts. And same trend, you can see that as you get darker, the pHs drop, and also the slopes increase, which means that they have more buffering power the darker you get on these caramel and crystal type malts. And so, you know, these graphs are a little weird because they're clustered in small areas, but I made these scales the same so you could see, so you could compare one type of malt to another. So as I move between these 3 graphs, you can see base malts, caramel malts, dark roasted malts. And if I go back and forth between the dark roasted malt and the caramel, you can see the darkest caramel malts and the dark roasted malts are all pretty much in the same general range. So dark roasted malts, unlike the first 2, there really isn't any correlation to color. They're all behaving pretty much the same, and they're behaving in a similar way as the darkest caramel malt. So there's a limit to how much acidity these are creating. Finally, I've got acidulated malt, because we used to use that at Ale Asylum to adjust mash pH. So it's nice to know how much acid it's going to contribute at that pH. So if your target pH is 5.3, you could follow that line up and say it needs about, or it needs about 200 milliequivalents of base to be added per pound of acidulated malt to move the acidulated malt to that pH. So you kind of apply that in reverse and say this is sort of how much acid the acid malt contributes at that pH to do your balance with the mesh. So when you factor in these grains, when you factor in your water, you're going to end up at a requirement for more acid or more base. So if you want to decrease your pH, you can use acid malt in the grain bill. You can add acids directly to your mash, phosphoric acid, lactic. You could add sour gout, which is sour wort. You could add calcium salts like calcium chloride, calcium sulfate, gypsum. On the rare occasions that you need to increase your pH, calcium hydroxide, which is slick lime, you could add baking soda, you can add soda ash, all those will raise your pH. Generally don't recommend calcium carbonate, even though it's the main contributor to alkalinity. It doesn't want to dissolve under mash conditions, so you're not going to do really any good adding that unless you're going to add it to your water and use carbon dioxide to get that to dissolve. So quick note about increasing pH. My general recommendation is to remove the alkalinity from all your water that you brew with, even if you're making dark beers, especially if you're in a production brewery that's brewing several different types of beer, possibly in the same day. You're constantly filling and emptying your liquor tank. Treating that water for individual recipes isn't very practical. So if your water ends up being lower in alkalinity than you would want for that mash, yeah, you got to add a little bit more base, and that's a tiny bit more wasteful, but the benefit comes during sparging, where now you've got your hot liquor tank water is nice and low, and it doesn't have much alkalinity. So even if you want a higher mash, higher alkalinity for the mash, you still want your sparge water to be at a low alkalinity. So kind of an argument in favor of just treating all your water to get the alkalinity out, and then making needed adjustments in the mash for each recipe. Talk a brief bit here about titratable acidity, often called total acidity. So, sour gout is something I didn't really think about until probably 2-3 weeks ago. I know New Glarus has done it forever. But I recently taught the water section for the malting and brewing science course, and one of the students asked about calculating that because he eventually wants to do that in his brewery. And so I went through the exercise of figuring out how to calculate sour gout additions, and it relies on titratable acidity, just like if you were making sour wort to make a sour beer. That TA number is useful for quantifying that sourness, and it's also useful for quantifying how much acid it's going to contribute if you wanted to add it to your mash or you wanted to add it to your kettle. So basically what you do is you take a 50 milliliter sample, and titrate it with 0.1 normal sodium hydroxide until its pH is 8.2. And then you do a little math. And I, for the sake of this talk, I wanted to convert it to milliequivalents per liter because that's the unit we're working in. Typically, it's going to be in, I believe, moles of hydrogen ions per liter. So that's going to be, I believe, 1,000 times less than the milliequivalents per liter, because it's millimoles instead, or it's moles instead of millimoles. And a milliequivalent per liter is a millimole of charge. So we've talked a lot about mash pH. I'm almost done. I'm not going to keep you here all night. But I wanted to talk a little bit about wort pH as well. So if you're going to do, if you want to acidify your wort in your kettle, to achieve a certain pH, you're going to have the same tools at your disposal as the mash pH. Unfortunately, there's not a whole lot of information out there about how to adjust the pH of your wort, aside from some rules of thumb. If you look at an old like Siebel book, for example, you'll see add this much amount of acid to get like a 0.1 pH drop, and that's really based on light colored, approximately 12 Plato wort. But we're brewing beer with all different ingredients at all different gravities. So I've got a working theory that I can use brew house efficiency to determine kind of the effective amounts of each grain in the wort, and then use the same kind of analysis as the mash to get this to give me a pH. And I did this once at Octopi. We had a need to figure out how much acid to add to a given batch to achieve a target pH, and it got us close. So I think it's got some promise. And if you guys want to bear with me for a second, I will show you kind of how that works in practice. So let me get out of that for a sec. So if you navigate to this website, and I can send this to you, just get in touch with me if you don't get it from watching this. I've got a whole bunch of spreadsheets that'll do water, mesh, and kettle calculations. And some of them are standalone, some of them are incorporated into recipe documents. And they make it really easy to do these calculations. I do want to give you guys the disclaimer here that it's all based on my test with my grains. So when I use it, it works pretty well, but your mileage may vary. And then the calculations for kettle pH and sour wort are very, very preliminary. They're in the early stages of development. So treat those with a grain of salt. But I am going to flip my share here. Is it actually going to let me do it? Oh, this is interesting. There it is. All right, wasn't giving me the option. So can you guys see this? Can you see
Hey,
the
Joe. Yeah, absolutely. Can you drop that link in the chat just so it's
Yes.
readily available?
Yeah, and
I mean, that's a start. We'll include it in the notes, but yeah,
Sure.
if you could drop that way, people take a look at it. Thank you.
yeah, I will do that right now because my attention span is approximately 10 seconds. There you go.
It's
So,
a really
Well,
good
thank
link,
you.
by the way.
hopefully that works.
Awesome. Agreed.
So you can see in this thing that I've got a beer recipe in here. I've got, it basically looks like an amber ale. I've got some pale malt. I got some caramel 60. So we're going old school here. Enter a few variables like what are my mash volume and temperature, some water runoff parameters. If I want to use acid malt, I can adjust based on some COA specs. I've got some sour goot numbers in here. And then down here, I've got my water. So I got my pH there, how much I want to treat, what kinds of lactic acid I want to use for the alkalinity removal mash kettle. I can enter in liquor tank calcium salts, mash calcium salts, or various salts, not just calcium. The source water goes in here. If I want to do RO, I can do this dilution water number. I've got things here for kettle treatment. If I want to achieve a calcium target in the kettle, I can decide what percentage of chloride and sulfate I want to use, and it'll automatically spit out more numbers to hit that target. So what I wanted to do is just show you a couple of quick scenarios here. So right now, to have a target mash pH of 5.35, it's calling for 149 milliliters of 85% phosphoric acid. And this is on top of a lactic treatment in the liquor tank of almost 1700 milliliters there. So if I wanted to use acidulated malt, I could go up to this pale malt row and say, hey, I want to replace that with acidulated malt. So take a look at these weights. I'm going to hit a Y. It's going to drop my weight from 759 to 749. It's going to tell me to use 10 pounds of acidulated malt. And the phosphoric acid requirement goes away. So it's letting me choose between different treatments here. If I wanted to use lactic in the mash, lactic in the mash at 88%. Now I've got 192 milliliters instead of 149 of 85% phosphoric. So you can adjust things that way. If I scroll down here to the kettle, if I want to do sour goot for the mash, I can type that in. It'll change the name of this to sour goot, and it'll tell me to use half a gallon of sour goot to get this mash where I want it. If the TA is 100 milliequivalents per liter. So if we were looking in terms of like what we would see grams per liter as lactic, that would be a TA of 9, if that's the language that you happen to speak. And so, yeah, you can do that for the kettle. If I've got a target mash pH of 5.35, I'm using straight Madison water, acidulated with lactic. It's going to kick out this number that says, oh, I think your pre-boil pH is going to be 5.43. This is the stuff that's new. So this is the stuff that I'm working on that I'd like to get dialed in. And I think this has potential to be pretty cool. But I can say I want my post-boil pH to be 5.1. it's going to tell me to add 49 milliliters of phosphoric acid. And then it's going to spit out what it actually thinks I'm going to get for a pH. Because if I put that pH target to 5.2, it's like, nope, your water, your post boil is already going to be lower than that, even if you don't add any lactic or any phosphoric. So, you know, it gives you that little bit of feedback loop. So, you know, hopefully this ends up being a pretty powerful tool that lets you look at different pHs of the process, and you can, you know, if it works out, it can be applied to anything as long as you know what the inputs are. So, you know, I just wanted to take a quick minute and show you that. I know it's not very intuitive, so if this is something you are interested in learning to use, just reach out to me. I'd be happy to go over it with you in greater detail. So yeah, that's pretty much my spiel for the day. I'm going to unshare this screen. Stop share. Yeah, so if you guys have any questions for me or for Matt, now's the time.
Well, Joe, I want to comment. That was a great presentation. Both you guys, I enjoyed it a lot. I'm going to have to say, Joe, that I brew a lot like you. I use RO water when I'm brewing a dark beer. My water is 400 ppms of alkalinity and 375 hardness.
Yuck.
So, you know, so when I brew a I do Russian Imperial Stout barrel aged, you know, and they're big beers, 10 to 14%. So, you know, there's 250. I'll use half my house water and half RO water and then the pH is still around 5.5, which is good for a dark beer. But my question to you is, like, I know that RO water is corrosive as all get out. And I noticed on your spreadsheet that your HLT was treated with the calcium salts, and Epsom salt and sodium chloride. Do those minerals that you add to that, are they enough to keep it from being as corrosive as it is?
So I'm going to reshare the screen for a second, because I'm actually not treating with those. I've got these here as salts that you can add. But if you look here, these are the rates to add them, and they're all 0. So I'm not adding those at all. But
okay.
if you look at my dilution water, I've also got that set to 0. So for this is straight Madison water treated with lactic acid. If I wanted to use 50-50 blend, I would set this dilution ratio to 50. And you can see it's still calling for lactic acid, but not nearly as much, because the dilution gets my alkalinity down to about 113 in terms of parts per million as calcium carbonate. And that's still got plenty of ionic content. Now, if I make this dilution 100%, or sorry, that was 10. If I make this 100% take 2, lactic acid requirement goes away. I've got a total alkalinity of like 3 parts per million as calcium carbonate. And this water is going to be extremely corrosive. So what I want to do, and really if it's, I guess if you're heating that water in a kettle, yeah, that's going to be a problem, potentially over time. So I want to pull up a conversation that I had. I'm not going to like share the screen or anything, but I want to do a really quick, like hopefully a 10-second search here for a conversation I had with John Palmer over email. Corrosion from RO water. His recommendation is to add about half of, he says an equivalent per liter, he probably means milliequivalent per liter of baking soda and calcium sulfate are his recommendations. I'm sure sulfate and chloride are interchangeable as far as that goes, but he's recommending a half a milli equivalent per liter each of baking soda and calcium sulfate. So let's do another really quick exercise here. Let's assume we're doing 100% RO water, and I'm going to put in some, I'm going to look at the mash water because I can actually do a sodium bicarbonate addition like voluntarily for that. It won't let me do it for the hot liquor tank because that's just stupid. So 50, but apparently it's not stupid if you're going to use straight RO water. So if I look at this mash water, This is telling me I've got like 0.58 milliequivalents per liter of calcium. I guess that's not necessarily, yeah, that would be like saying that same milliequivalent of calcium sulfate because it's based on the ionic charge. So one of the cool little tricks you can do in Excel is you can click on the cell that you want to be a certain number. You can go to data. I don't know if you can see what I'm doing right now or not. Oh no, it would be this data. And there's a thing called a what if analysis. You do a goal seek, you set that cell to 0.5 and you set it there by picking what cell you want to adjust. So I'm going to adjust the calcium sulfate. And now there we go. So if I wanted to do 40 barrels of mash water, I would need 54 grams of calcium sulfate to get that number. So if I scroll down here again, you can see that number is 0.5. So I can do that same for the total alkalinity. What if analysis, goal seek 0.5 by changing the baking soda. So there you go. So in terms of grams per barrel, it would be 5.1 grams per barrel. So call it 5 of calcium sulfate, 5 of baking soda, and you can convert that to gallons by dividing by 31. So per gallon of water at home, you're adding like 0.16 grams of each. So not much. Yeah, to counteract that. It doesn't take much to counteract that corrosivity of reverse osmosis water.
It sure cleans the bottom of that kettle though when you let it sit.
Sorry, what was that?
Chris.
See you, Chris.
I said when you let that water sit for, I filled my kettles with water and then I got called away for a weekend. And I told them, I said on Sunday, I got to leave early in the morning. I got to brew today. In 2 days. And the kettles were cleaner than they've ever been. I use induction burners. And there's that spot on the bottom that gets that blue, and it was completely gone.
Yeah, and you probably stripped off the passive layer of that metal. So
I repassivated it, but I got done brewing, and then I did that brewer's friend.
Sure.
Joe, when did you upload this new sheet that you have on that?
Last night at like 11:30.
Sweet.
Yep.
Probably gonna use the shit out of that.
Yeah, I hope it's worthwhile.
I feel like one real quick point though to piggyback on the end of what Joe was saying. This is probably more for people that are watching this after the fact instead of the people that are here, but I know a lot of the people that are here can attest to the value of this book right here as far as what a lot of Joe was, I think that's the book you referred to, right, Joe?
Yes.
Yeah, it's lots of good stuff in there and it comes from a practical point of view. Just thought I'd throw that out there.
Yep.
It's not a fun read, but it's good.
Joe's spreadsheets are like pure magic.
Thank you, Eric.
Hey, anytime.
Okay, anything else or are we cutting to happy hour / hot goss time?
I think I'm good to cut the hot goss. I can't stick around long. Maybe I got
Same.
or something.
Yeah, I can't either. Okay. Steve, we don't